Hi, everybody. I'm Patrick Ames. You know my name. So I'm working as a principal engineer at Amazon. Been working there for about 10 years now. Most of my work is focused on data lakehouse management for a centralized data lake that serves all of Amazon's various business units. A lot of it is focused on business intelligence use cases at Amazon in particular. I'm also serving as a member of the Ray project on GitHub. For those of you that know about Ray or have used it before, great. For those of you that don't, it's all good. We'll get into that a little bit later in the talk. And yeah, we're going to talk about some cool stuff we're doing related to streaming data and some of the challenges we've encountered with it when integrating our existing streaming pipelines with Iceberg, and the challenges we're encountering as we're starting to adopt Iceberg as an additional standard lakehouse format in Amazon centralized data lake. And some of the integrations we're doing with Beam and Ray along the way via the Ray DeltaCAT ecosystem project. So to give you a quick overview of what we're going to talk about here, I'm going to first give you a brief history of Amazon Business Intelligence, at least as I know it. Right, I've been at Amazon for about 10 years. Business intelligence has a longer history than that at Amazon. So you're going to get the history as I know it, the 10-year history, basically. And then we'll go over Iceberg and DeltaCAT, talk about what those are, compare and contrast. We're going to talk about what we found to be the streaming problem when integrating our streaming pipelines with Iceberg at Amazon. And we're going to talk about the open Exabyte-scale solution that we're working on and trying to make available to all of you so that you can also process streaming pipelines with Iceberg at any scale and hopefully with acceptable latency. And then we'll quickly review the current state of that and future work that we're planning on doing. So getting into the history of Amazon BI here. So I joined Amazon in 2016. And at the time that I joined, Amazon was in the midst of petabyte scale, specifically I think it was about 50 petabytes, Oracle data warehouse deprecation at the time. And you have a quote there, when we finally turned Oracle off and deprecated it officially across the company. Werner Vogel's our CTO and Andy Jassy are now CEO, giving out a quick, at the time, tweet about the project there. So this was one of the largest, if not the largest, Oracle data warehouses in the world. The first project that I worked on was literally writing the distributed systems and services that would move all the bytes out of these Oracle tables into S3. It should be like a simple copy command, right? How hard could it be? But those of you that have been through this know that it gets a lot more complicated than that. I don't know. It took us probably like 20 retries of copying the full Oracle data warehouse before everything actually checked out and different systems could consume it. So yeah, but we accomplished our goal. We decoupled storage and compute, and our initial compute subscribers that we replaced Oracle with, right? All the data went into S3, Parquet files, delimited text files. I know Parquet is cooler than delimited text, but delimited text is super sticky. We still use it today. And Amazon Redshift and Hive on EMR were our first compute frameworks. And then in 2018 to 2019, we started seeing the first semblances of lakehouse formation here. And this was, I think, about the same time the folks at Databricks were working on these sorts of things, and various other people in the industry were working on it, and around the time that the term lakehouse was coined, I think was shortly after this. So it wasn't called a lakehouse at the time. But we have a quick diagram there on the right that kind of shows how very particular and special process inside of our lakehouse worked, called compaction. And the reason that we did compaction was because in our new data lake, again, we decoupled storage and compute, we wanted people to be able to bring their own compute frameworks, like say Redshift or Spark, over to our data lake and quickly consume whatever we had there. Well, what we had there, so you can see in the diagram on the left, was a bunch of change data capture logs of S3 files that said, hey, insert these records. Hey, here's an update, so find matching things by some merge keys, or delete these records, find deletes to apply by matching predicates. Well, it's a lot of work for downstream consumers to actually stitch things together and read them if they have to reapply this change data capture log every time. The diagram on the right there shows the very simplest case of compaction, where you just have append-only records that you're concatenating. So you're concatenating small files into larger files to optimize your reads. The slightly more interesting and complex case of compaction is what we'd call upsert-based compaction. And we're using Apache Spark for this at the time. And upsert-based compaction is saying, hey, insert the record if it doesn't exist, and update it if it does exist according to some like primary key. As your tables grow to like petabyte scale, it becomes very computationally expensive to actually find whether or not there's duplicates, especially if you're doing it in any naive sort of way. And we started to find that Apache Spark, our compactor at the time, using pretty plain vanilla implementations that we had on EMR, was starting to break the bank and incur unacceptably high latencies. We were starting to violate SLAs in terms of data delivery to downstream consumers who needed to consume directly from the compacted table. So that leads us to looking for other solutions. And Ray was a solution we landed on, partially because it came out of the same lab at UC Berkeley as Spark, or rather the successor to that lab. Spark came out of AMP lab at UC Berkeley, and this came out of Rise lab, but led by some of the same professors that worked on Spark. But Ray's focus was actually initially on more machine learning. But in order to focus on machine learning, they had to make a very general purpose distributed systems compute framework. So it fundamentally consists of two key primitives: a distributed function called a task, and a distributed class, which they call an actor, for stateful distributed operations. But Ray, since it's focused on machine learning, primarily focused on providing Pythonic APIs to people. And this also checked another box for us, because in the old Java ecosystem, we were getting increasing complaints from data scientists, ML engineers, that it was very hard to integrate their Python applications with our data lake. So that was a secondary reason for us to look into it, aside from seeing if we could use it to optimize our compaction problem. So going into 2019 to 2023, we started working on replacing Spark with Ray after some initial promising data points we got that we could actually do this compaction operation a lot faster on Ray. It would also serve as a very useful proof of concept about how efficient and scalable of a distributed system Ray was in general. So the diagram on the right there shows how we used Ray in shadow mode to compare the results versus Spark. We'd basically have all of our different query engines, from Spark to Flink to Redshift to Athena, query the compacted merged tables that were produced by both Ray and Spark. We'd have a data reconciliation service, compare the results, make sure there were no meaningful differences between the results. And we'd also have a statistical data quality service that was also based on Ray, making sure all the key statistics lined up. In the end, we were able to reduce the cost of compaction in our now Exabyte-scale data lake by 82% on an annual basis, which is equivalent to saving about $120 million a year if you were like just a typical external user of EC2 on-demand instances. Obviously, internal pricing at Amazon is a little bit harder to derive as the owners of the hardware itself. And there's a quick historic graph that we captured from January of 2024 to March of 2024. And this trend has continued to today, showing what we call the Ray instance minutes that it took to compact a gigabyte of data compared to Spark, and that approximate 82% savings that has continued from that point in time until today. And then from 2024 to 2025, we started working on Ray exclusivity. So we are starting to shut off the Spark shadow compaction side of the world and move more exclusively onto Ray as a more efficient solution for maintaining all of our tables. This compaction operation has to run after nearly every write to all of our tables, so it's a very important operation for us to get right and to get as efficient as possible. And we've contributed an open source implementation of the compactor that we wrote to the DeltaCAT project. And that's a project we're currently incubating in the Ray ecosystem to be a portable Pythonic data lakehouse that integrates very natively with various Pythonic compute frameworks and Ray in particular. So it includes various components that you need to build a lakehouse, and Amazon has internal implementations of all these components that we're gradually trying to put out into open source equivalents that work on more than just AWS. So that's catalog, various compute functions. Those of you that are familiar with Iceberg know they have various stored procedures to manage your tables. We're re-implementing a lot of those on Ray. Storage formats, both metadata and data equivalents and file format equivalents, especially for multimodal data, and synchronization capabilities that let you say, hey, I've got this data here. I want to put it in another data lake format or another data warehouse. Version 1 of DeltaCAT is used in production at Amazon, but it's also overfit to what we do at Amazon. So not exactly ideal for external use. And we're currently developing version 2 right now so that it is not so overfit to AWS and Amazon internal use cases and can apply to things like Iceberg and integrate better with the rest of the open source ecosystem. So right now, we're working on lakehouse unification. The diagram on the right shows, again, a quick example of that. One of the key things is if you start with 2 Parquet files, say you do hash bucketing on it, split those Parquet files apart, we want to reuse the hash bucketed Parquet files that we produced across as many data lake formats as we can. And DeltaCAT would manage the synchronization process for that, saying, okay, I'm not going to copy the Parquet files. I'm just going to create and register the equivalent metadata in Iceberg, in Hoodie, in Delta Lake, wherever it will fit. And we're also working on batch and streaming compute integration, going back to unifying the compute side of the world and getting into why projects like Beam are relevant to us, and putting out an open source implementation of Iceberg table maintenance using Ray and DeltaCAT. So the quick DeltaCAT overview is basically that you have a data producer writing either tabular or multimodal file formats, anything that's readable by the distributed data set formats there in the blue box on the right. So that's Ray data, Daft, PyArrow, Pandas, NumPy, Polars are some main things that we do distributed versions of to read. And if those can read your file formats, we'll read it, and then we can register it in an Arrow native format with relatively Arrow native metadata like Arrow schemas, et cetera, inside of our DeltaCAT catalog. And then you have kind of a closed loop there that works well for Pythonic data consumers. But for the historic and legacy world, where you have people still consuming with Spark, Trino, Flink, SQL, what probably you all are using today, we also offer that synchronization capability to synchronize just the metadata over to Iceberg as our first format. We'd like to add on to that Delta Lake, Hoodie, and other formats later. And so Iceberg overview, I think you already got a quick overview of Iceberg. We'll focus a little bit more on the table metadata here and the catalog. So at a very high level here, you have that diagram showing you how you have a table metadata file, snapshot files, manifest files, and data files. And then you need a catalog to basically keep track of all the top level table metadata files. Like AWS Glue is an example of a catalog on AWS you can use that keeps track of these things. And here's what an Iceberg table directory looks like. You have a data directory, a metadata directory. You look inside the metadata directory. Those first 3 files on the top are table metadata files. You have a manifest file, which is Avro underneath that, and then a snapshot file, which is Avro as well. And then the data directory, if you look into that, this one, again, we've used hash bucketing, 1,000 hash buckets. And you can see the kind of Hive-style directory naming it uses there by default with the writer we use, which I think was Spark. And then inside of a partition directory, you can see the Parquet data files for that particular partition. And I want to talk a little bit about Iceberg deletes in particular, since they're pretty key to the problem we're having. Iceberg offers 2 types of operations, basically. You can append data, or you can delete data, right? And through those mechanisms, you can do things like upserts, because it's nothing more than appending and deleting data in the right order. So Iceberg offers equality deletes, which just say, go fish. I'm going to give you the predicate. I'm going to say, hey, find the records that match these values for this column, and the consumer has to incur a lot of cost and latency to find it. But it's easy for the producer to write. Then it has positional deletes. This is what frameworks like Spark prefer to write. It says, hey, the writer has already resolved where the duplicate positions are. Oh, it's in row index 0 of foo.parquet and row index 1 of foo.parquet. You don't have to go fish as a reader. Just ignore those record indices. So more efficient on the read side. And then in Iceberg v3 spec, they're also introducing Iceberg delete vectors, which are binary representations of the same, using bits to denote which records are deleted and kept. And now we have Iceberg copy on write, often abbreviated as COW. So you have a copy on write data producer. He's a rich guy because copy on write data production is very expensive. He's going to, every time he writes to the table, rewrite all the data files in the table to materialize all the deletes. And then you have the copy on write data consumer just reading very cheaply, very quickly from all the data that the data producer went through the effort of materializing. Then you have Iceberg merge on read. So a merge on read data producer will produce positional or vector delete files, and a merge on read data consumer will have to apply the deletes on read. They're not materialized. And then you can later run a data file rewrite. There's a stored procedure for this in Spark and Iceberg today that will let you materialize all those deletes into your data files and again, read them more cheaply. And this leads us to the streaming problem we discovered. Well, with merge on read tables, streaming frameworks like Flink prefer to write equality deletes because they're cheap and fast, but they lead to expensive reads. And as we'll see here, that means it may cause even out-of-memory errors on read. And then batch frameworks like Spark want to write positional deletes or binary delete vectors, and this leads to moderately expensive writes and cheaper reads, and that makes them less practical for high-frequency writes at terabyte or petabyte scale. Yeah, they're high latency, and they may even produce irresolvable write conflicts if they conflicted with another writer and that writer took away a file that you're trying to point a positional delete to. So copy on write tables also aren't really great for streaming because, again, it's just very expensive to rewrite all the data files every time you're going in, and often too high latency, especially as your tables grow very large. And so we have this interesting 5-year history of issues and PRs raised in the Iceberg project, talking about this, saying, hey, data file rewriting on Spark job fails with out of memory, and Spark rewrite files action out of memory. People saying we need to add an action to rewrite equality deletes as positional deletes to prevent these problems. They were running out of memory because there were too many equality deletes that had been written to the table by something like Flink, typically. And we had bumped into this problem as well at Amazon because we were chiefly writing equality deletes to all of our tables before we were using Iceberg. So this is basically the state you're left in. You have a data producer on Flink who can happily write equality deletes all day, but then you've basically broken, at least at scale, you have broken your merge on read data consumers and your copy on write data consumers. And so to go back and address that original issue from 2020, we have written a job inside the DeltaCAT project on Ray that takes advantage of our previous compaction work, which we saved 82% of cost over versus Spark, to convert those equality deletes into positional deletes on petabyte scale tables and across an exabyte scale catalog. And today, going to Beam, Beam has Iceberg integration. And if you just use Beam to append data to your tables, you'll be happy. It's a little bit of a limited feature set, but you can write data and just append, and data consumers can happily read. And one interesting capability we've added on top of Beam today, and we've added an example, which we'll link to in just a moment, is the ability to now treat these data appends that Beam writes as upserts. So you can also do that. You can say, hey, you appended a bunch of data. Let me give you some merge keys along with that data you appended, and you can come back and rewrite it as an upsert instead of having to do it yourself. So that's available for experimental use in open source today. And you can then also go and throw Spark at it, and it can very efficiently rewrite and materialize all those data files. Because again, we're using positional deletes or delete vectors inside of Iceberg to actually process beam appends as upserts. So the current state is we're testing with petabyte-scale production Iceberg tables over at Amazon, and by Q4 of this year, we're going to start production onboarding to exabyte-scale production data catalogs over at Amazon. And our Python converter job is ready for experimental use. I don't encourage you to take it into production for various reasons that we could talk about right now. Like, wait for Amazon to go into production with it first, and let them burn the risk. And then we'll come back and give the green light. But you can use it, and it seems to be functional in my tests. But yeah, you guys can go ahead and use that out there today. You can run it manually, you can run it automatically, you can run it locally, you can run it on a distributed array cluster. Your choice. There's a QR code there that'll take you right to the example link that's also written right below it. And future work, if you guys are interested in this domain of continuing to improve streaming for Iceberg, there's some GitHub issues. Please +1 them if you'd like deeper and further integrations with Flink and Beam, and to make streaming on Iceberg work increasingly better. And yeah, that's about it, guys. So thank you for being here. You can reach me on the Ray Slack, my name. So there's my GitHub info and the DeltaCAT GitHub info. So yeah, thanks.